steam flows from nozzles at the rate of 0.2 kilogram per second and speed 900 meter per second. It then enters the rotor of single-stage impulse turbine with equiangular blades. The flow leaves the nozzles at an angle of 70 degrees. The mean radius of the blades is 120 millimeters and the rotor speed is 18,000 rpm. The frictional loss in the rotor blades is 15% of the kinetic energy of the relative motion entering the rotor. Draw the velocity diagrams at the inlet and outlet of the rotor with properly calculated values of the inlet and outlet flow angles for the relative and absolute velocities. B. Find the power delivered by the turbine, and C. Find the rotor efficiency. Okay, as usual, before we start solving this problem, we should mark or find the key information from the question. Okay, first, the flow rate is 0.2 kilogram per second and the steam speed is 900 meter per second. And it is a single stage impulse turbine with equiangular blades. Okay, the steam leaves the nozzle at angle of 70 degrees and the mean radius of the blade is 120 millimeters. And the rotor rotates at 18,000 rpm. And the loss due to frictional loss is 15% of the kinetic energy. Okay, so now we want to solve the problem by first we want to calculate the blade speed. Okay, so the blade speed U can be calculated using this equation. U equal R specific or not specific, the rotational speed. Okay, the rotor speed. R is the radius of the turbine. Okay, so this is a straightforward calculation. We have given the radius of the turbine in the question, and we also have the rotational speed of the blade in the question. So we just plug in the value of radius 0.12 and 18,000 rpm inside this equation. Using the this equation, we will get the blade speed is equal to 226.2 meter per second. Okay, next we want to calculate, this is the preparation to get the preparation or the needed value to calculate the flow angles, okay, and the absolute velocities. We want to solve question A. Okay, and then the axial velocity is equal to, we need to do some trigonometry here. Okay, Vx2 equal V2 cosine alpha 2, which equal V2, we know from the question, 900 meter per second, and alpha 2 is 70 degrees. Okay, alpha 2 is 70 degrees. So we plug in the value inside this equation, you will get Vx2 equal 307.8 meters per second. Okay, and the tangential component of the absolute velocity at the inlet of the rotor is Vu2 equal V2 sine alpha 2. We will get 845.7 meter per second. And the tangential component of the relative velocity entering the rotor is WU2 equal VU2 minus U equal 845.7, which we just calculate up here. In this case, WU2 is equal VU2 minus U. We have calculated VU2 and we have calculated U2. We just plug in those values here and you will get WU2 equal 619.5 meter per second. And so that the relative flow speed, since Wx2 equal Vx2 comes out to be W2 equal square root of W2x2 squared plus WU2 squared. Plug in the values and you will get W2 equal 691.8 meters per second. And the inlet angle of the relative velocity is therefore beta 2 equal tangent minus 1 WU2 over WX2. So the inverse tangent of this value, you will get beta 2 equal 63.6 degrees. Since 15% of the kinetic energy of the relative motion is lost at the exit, the kinetic energy of the relative flow is 1.2 W3 squared. This is the kinetic energy equation. Okay, this is the kinetic energy equation, equal 1 over 2, 1 minus 0.15. This is the efficiency, W2 squared. Okay, so if we solve this equation, you will get, or we will get W3 equal 637.8 meters per second. Okay. And for equiangular blades, so we have two different conditions. One is equiangular blades, which mean beta 3 is equal minus beta 2. Okay, beta 3 is equal minus beta 2. This is called equiangular blades. For non-equiangular blades, beta 3 and beta 2 not necessarily have the same inverse value. Okay, so in this case, the turbine have equiangular blades. So beta 3 is equal minus beta 2. And the axial velocity leaving the rotor, we can calculate using this equation. Wx3 equal W3 cosine beta 3. We plug in all values that needed in to solve this equation, we will get Wx3 equal 283.8 meters per second. And the tangential component of the relative velocity is Wu3 equal W3 sine beta 3, which equal minus 571.2 meters per second. Okay, here I want you to be careful about the positive and negative sign. Okay, because beta 3 is equal minus beta 2, don't forget to put negative sign inside here. Okay, otherwise you for example, if you don't put this negative sign, you will get Wx3 as negative values and Wu3 as positive values. And when we do further calculation, we will get a wrong answer because of when we sum up, we add or we sum up the power or the velocity, we will get different value. So be careful of this positive and negative sign. And the tangential component of the absolute velocity becomes Vu3 equal U plus Wu3 equal, we plug in the values, you will get Vu3 equal minus, okay, here the Vu3 will equal minus 345.0 meters per second. Okay, if you don't put a correct negative and positive sign here, you will get a different value of Vu3 here. Okay, so be careful. Okay, so this is the velocity triangle at the inlet of the blade, and this is at the outlet of the blade. Okay, so if you the best practice is to draw or to sketch these velocity triangles first before we solve the problem, so that you know, for example, how we get this kind of this equation, and this all these the velocity equations. Okay, if you draw the velocity triangles, this velocity equation will you can easily understand why we use this equation. Or you don't have to memorize this equation, you can find it by looking at velocity triangles. Okay, or by solving these velocity triangles using trigonometry, you can get the velocity equation that needed to solve this question. Okay, hence with Vx3 equal Wx3, the flow angle at the exit is alpha 3 equal inverse tangent Vu3 over Vx3, and we will get alpha 3 equal minus 50.6 degrees. And the velocity leaving the rotor, V3 here, we will get a V3 equal square root of Vx3 squared plus Vu3 squared. We have the value of Vx3 And also we have the value of VU3. Plug in those values inside this equation, we will get V3 equal 446.7 meters per second. So now we can put the flow angle at the exit value and the velocity leaving the rotor value inside the velocity diagram to solve or to complete question A. Okay, so don't forget to draw to sketch this equation with the values, the ask values inside the question. Okay, all right, so we want to solve question B. The specific work done on the blades, uh, is obtained using this work equation. You will find this equation over and over again in any turbine. Okay, not only steam turbine, but in any turbine we will do this similar calculation. Okay, we have the value of U and VU2 and also VU3. We just plug in all those values inside this equation. You will get the specific work done on the blades is equal to 269.3 kilojoule per kilogram. And the power delivered, sometime they use this notation, but sometimes we just use P equal m dot multiplied by specific work. Okay, m dot is the mass flow rate 0.2, and specific work we just calculate up here, plug in here, and we will get the power delivered by this turbine is equal to 53.87 kilowatt. And next we want to solve question C, the kinetic energy leaving the nozzle. We use kinetic energy equation. Okay, half of V2 squared is equal half of V3 squared. Okay, 900 is V3. And we can solve V2 in this equation. We will get V2 equal, I'm sorry, it's not, this is not V3, this is V2. We just want to calculate the kinetic energy leaving the nozzle. So the kinetic energy leaving the nozzle is half V2 squared. So we plug in V2 values here. We will get the kinetic energy leaving the nozzle values as 405.0 kilojoule per second. This is another straightforward calculation. And the rotor efficiency is therefore becomes, the rotor efficiency is equal specific work over the kinetic energy leaving the nozzle, which values we have just calculated here and here. I'm sorry, not here, here. So we plug in those values, we will get the rotor efficiency is equal to 0.665, or we can also write in terms of percentage, which is 66.5%. So efficiency can be written in terms of dimensionless number here or in terms of percentage. Okay, next we will look into gas turbine example. At inlet to the rotor in a single stage axial flow turbine, the pressure is 1 atmosphere. The the magnitude of the absolute velocity of fluid is 610 meters per second. Its direction is 31 degrees as measured from the cascade uh, front in the direction of the blade motion. At the exit of this rotor, the absolute velocity of the fluid is 605 meters per second, directed such that its tangential component is negative. The axial velocity is constant, the blade speed is 605 meters per second, and the flow rate through the rotor is 5 kilogram per second. A. Construct the rotor inlet and exit velocity diagrams showing the axial and tangential components of the absolute velocity. And B. Evaluate the change in total enthalpy across the rotor. And C. Evaluate the power delivered by the rotor. D. Evaluate the average driving force exerted on the blades. E. Evaluate the change in static and stagnation temperature of the fluid across the rotor, assuming the fluid to be a perfect gas with Cp equal 1148 joule kilogram Kelvin. And F. Calculate the flow coefficient and the blade loading coefficient. And are they reasonable? Okay, in the question, it is given, some value is given, the V2, alpha 2, V1, U, and M dot. We want to find delta T naught, P, and this angle. Okay, now we want to look into the solution quickly. For the axial and tangential velocity, the components at the inlet to the rotor are, I don't sketch the velocity triangles here, but you can try to sketch the velocity triangles and you will uh, understand why we use Vx equal V2 cosine alpha 2 and Vu2 equal V2 sine alpha 2. Okay, so V2 is given in the question, and alpha 2 is also given in the question. So we get Vx equal 295.7 meter per second and Vu2 equal 533.5 meters per second. At the exit of the rotor, cosine alpha 1 is equal to Vx over V3. So if you want to find alpha 3, we can find alpha 3 using the inverse cosine of 295.7 over 305. So we will get alpha 3 is equal to minus minus 14.16 degrees, and Vu3 is equal V3 sine alpha 2. We have we plug in all values that we know and we will get Vu3 equal minus 74.6 meter per second. To construct the velocity diagrams, the relative flow angles are needed. First, the relative velocity components are Wu2 equal Vu2 minus U, and Vu2 is equal 533.5 and U is equal 305. We will get Wu2 equal 228.5 meters per second. And so that we can calculate beta 2 by using inverse tangent Wu2 Wx over Wx2. And we will get beta 2 as 37.7 degrees. The relative velocity component after the rotor okay, this is WU2 is the relative velocity entering the rotor, and this is leaving the rotor. WU3 is the relative velocity component leaving the rotor. It's equal VU3 minus U equal minus 379.5 meters per second. And we know that for this condition, Wx3 is equal Vx3. This is mistake. Okay. So that beta 3 is equal inverse tangent Wu3 over Wx3 equal minus 52.08 degrees. So now we have solved question A, but remember to sketch the velocity diagrams and put the needed values inside the diagram as asked in the question. Okay, now we want to solve question B, which asking the drop in stagnation enthalpy. But before that, there are two ways to calculate the drop in stagnation enthalpy, which equal the specific work. Okay, specific work equal the drop in stagnation enthalpy. Okay, the value of specific work is equal the drop in stagnation enthalpy. So we can calculate specific work using this equation, and we can calculate drop in stagnation enthalpy using this equation. But since we don't have the enthalpy values given in the question, so we need to calculate the drop in stagnation enthalpy using the specific work equation. So we have the specific work equation, W equal U VU2 minus VU3. Okay, so we know we know VU2 and we know VU3. So we will get the specific work equal to 185,480 joule per kilogram, which is equal the drop in stagnation enthalpy, the same value. Okay, so we solve question B. And next, question C, the power delivered by the turbine is equal this is not equal, this is should be multiplied. Okay, m dot multiplied by specific work, we will get the power delivered by the turbine is equal 92.7 megawatt. And then the force on the blades, the force on the blade can be calculated using this equation. Force on the blade equal power over U. So we plug in the value that we have calculated before this, and we will get the force on the blade is equal to 3040 Newton, which solve question B. And the drop in the stagnation temperature, the drop in stagnation temperature T02 or T02 minus T03 is equal specific work over the specific heat. Okay, specific work we had just calculated before in previous slide, and specific heat value is given in the question. So we will get the drop in stagnation temperature is equal to 161.6 Kelvin. And the drop in static temperature, okay, the drop in static temperature T2 minus T3, which also equal T02 minus T03 minus 1 over 2 Cp V2 squared minus V3 squared. We have these values calculated up here, and we just need to calculate this value by plug in V2, V3, and Cp values inside this equation. Okay, and again, be careful with positive and negative sign. Otherwise, you will get a different value. Okay, and always remember, in solving problem, always write down the general equation before you put the values. Okay, always write down the general equation before you put the values, because this general equation could give you marks if your values is wrong. Your value, some of the values inside the equation are wrong. Okay, if you straight away writing the wrong value, it is difficult to give you mark. Okay, a good practice, even though if you are not concerned with mark, is to write down the general equation. Okay, write down the general equation, and then after that you plug in the values, write again the equation with the proper value, and you will get here the drop in static temperature is equal to 40.0 Kelvin, and the flow coefficient and the blade loading coefficient are, okay, the flow coefficient equation is equal to Vx over U equal 0.969 0.969 or 97, almost 97%. So the flow coefficient is almost 97%, and the blade loading coefficient is 2, which is a reasonable value for a gas turbine. Okay, these two values are reasonable values for gas turbine.